Welcome back to part 2 of our deep dive into the chemistry of your brain right here on Life and Learn. In part 1, we explored how neurotransmitters like dopamine, serotonin, GABA, and others shape our motivation, mood, calmness, and memory. Now, in this next chapter, we're peeling back the layers even further to understand what makes us bond and trust. Hint, it's not just personality, it's oxytocin. Why antihistamines make you sleepy? Hello, histamine. And why pulling an all-nighter makes your brain beg for sleep? Meet adenosine. We'll also look at what happens when things go wrong, how imbalances in these messengers contribute to conditions like insomnia, burnout, or brain fog. And most importantly, how your everyday choices can help restore balance, clarity, and calm. So take a deep breath, and let's continue our journey into the brilliant, buzzing world of your brain's chemical messengers. Oxytocin, the bonding hormone. Often dubbed the love hormone or cuddle chemical, oxytocin is famous for its role in social bonding, trust, and love. Oxytocin is actually a hormone that doubles as a neurotransmitter in the brain. It is released during intimate activities like hugging, cuddling, and orgasm, and in huge amounts during childbirth and breastfeeding to help a mother bond with her baby. It's the chemical thread that helps weave strong social connections. When you hug someone you care about for an extended time, let's say 20 seconds or more, oxytocin levels rise and you feel a sense of warmth, trust, and bonding with that person. It's literally creating a chemical signal in your brain that says, I feel close to this person. This is why hugging, holding hands, or snuggling with pets can be so comforting. Oxytocin is being released, reducing stress and fostering positive feelings. Oxytocin is also released during positive social interactions like teamwork or even just good conversation, helping build trust and empathy. It's a key player in pair bonding, romantic attachment, and parent-child bonding. Beyond making you feel connected, oxytocin has some other interesting effects. It can promote pro-social behaviors like generosity and affection and reduce fear responses in the context of social interactions. Some call it the social glue of society. For example, studies have shown people given a dose of oxytocin via nasal spray in experimental settings may exhibit increased trust in others during games or be better at reading emotional cues. It's even being researched for helping social anxiety and autism, though it's not a simple cure, or by any means. It's important to note oxytocin's effects can depend on context. It tends to amplify social feelings, which are usually positive like love and trust, but in some situations it might also increase envy or bias toward one's in-group. Human behavior is complex, and oxytocin is just one ingredient in the mix. Still, its reputation as the love hormone is well earned. It's strongly associated with affection, bonding, and the tender aspects of relationships. Physiologically, aside from bonding, oxytocin causes uterine contractions during labor and helps with milk ejection during breastfeeding. Fun fact, just seeing or hearing her baby cry can cause a mother's oxytocin to release and trigger lactation. In men, it's released during ejaculation and is thought to play a role in bonding there as well. In everyday life, oxytocin is that warm, fuzzy feeling chemical when you gaze into a loved one's eyes, when your dog excitedly greets you and you pet them, or when a friend sincerely comforts you. In all those moments, oxytocin is flowing and strengthening the social fabric between you. It's the biological reason why connection feels good and is so crucial to our well-being. Histamine, the wake-up and allergy mediator. You might know histamine as the culprit behind allergies, like when you take an antihistamine for a stuffy nose, but histamine also moonlights as a neurotransmitter in the brain, where it has a different job keeping you awake and alert. In the brain, histamine is produced by a small set of neurons in the hypothalamus, and it acts as a wake-promoting neurotransmitter, part of the system that maintains our alertness during the day. How do we know histamine promotes wakefulness? A big clue is that many antihistamine drugs for allergies cross into the brain and block histamine receptors, which often causes drowsiness as a side effect. If you've ever taken a first-generation antihistamine like diphenhydramine Benadryl, you know it can knock you out. That's because by blocking histamine, it's effectively reducing those wakefulness signals, allowing the sleep drive to take over. Histamine neurons in the brain are normally active when we are awake and virtually silent during sleep. They help you stay vigilant. In fact, histamine works in tandem with other arousal systems, like those using norepinephrine and orexin, to keep you from drifting off. Aside from wakefulness, histamine in the brain can also influence appetite and learning, but its strongest effect is on arousal. There's ongoing research into drugs that target the brain's histamine system for treating sleep disorders like narcolepsy, or even cognitive issues. Speaking of narcolepsy, it's primarily caused by loss of orexin, hypocretin neurons, but the histamine system is a neighbor of those neurons. And there's evidence that stimulating histamine receptors might help wakefulness in such conditions. In the rest of the body, histamine is released by immune cells known as mast cells and causes inflammation, dilating blood vessels, making tissues swell and irritating nerves. That's the allergic response, which is, well, uncomfortable. But in the brain, histamine's effects are more subtle and constant. It's not something you feel in a direct way like dopamine or serotonin. You won't think, wow, I feel so histamine-y right now, but if histamine was suddenly removed, you'd feel extremely groggy. Interestingly, the grogginess of sleep deprivation or the afternoon slump might involve histamine. As you stay awake for a long time, other factors like adenosine, which we'll discuss next, build up and push against histamine's wakefulness, making you sleepy. That's why taking an antihistamine on top of already being tired can be a double whammy for sedation. So, in everyday terms, think of histamine as a quiet but crucial alertness signal in your brain. It's like the steady drumbeat of wakefulness, and when you quash it, with a medication or by naturally winding down at night, you allow sleepiness to take over. The next time you have the yawns after an allergy pill, you'll know it's because you basically put your histamine neurons on mute. Adenosine, the sleep pressure builder. Ever notice that the longer you stay awake, the more you feel an increasing pressure to sleep? That sensation isn't just in your head, it's partially chemical, and adenosine is a prime reason. Adenosine is a neurotransmitter and also a molecular building block in cells that accumulates in the brain while you're awake and produces sleepiness, often called sleep drive. Think of adenosine as an hourglass timer for your wakefulness. As your neurons fire all day, they use energy in the form of ATP, and adenosine is one of the byproducts. Gradually, adenosine levels in the brain rise. Adenosine makes you feel tired by slowing down neuronal activity. It's basically sending a message that says, "You've been awake a long time, let's cool things down and get some rest." As adenosine latches onto its receptors in the brain, especially in regions that promote alertness, it inhibits them, making you drowsier and less alert. By the end of the day, if you've been awake many hours, adenosine levels are high and you feel that heavy-eyed, must-sleep-now feeling. This is your sleep pressure, and it's a big component of why we get sleepy, independent of any daily routine or darkness. Now, when you sleep, particularly during deep, slow-wave sleep, your brain clears out adenosine, essentially resetting the clock by morning. If you don't get enough sleep, some adenosine remains and you wake up still groggy with sleep debt. That's why a short nap can refresh you. Even a 20-minute snooze can slightly reduce adenosine and lighten the pressure. Here's where it gets fun. Caffeine. Caffeine is the world's most popular stimulant, and it works chiefly by messing with adenosine. Specifically, caffeine blocks adenosine receptors in the brain. Imagine adenosine is a key trying to fit into locks, receptors. to signal sleepy time. Caffeine comes in and jams those locks. It sits in the receptors but doesn't activate them, and it prevents adenosine from binding. So even though adenosine is still building up, it can't do its job of making you drowsy as effectively because caffeine is essentially putting tape over the sleepy buttons. This is why after a cup of coffee, you feel more alert. You've essentially tricked your brain into ignoring the adenosine sleep signal for a while. However, as the caffeine wears off, all that adenosine can rush in and bind, which is why you might have a crash or sudden wave of sleepiness once the caffeine leaves your system. If you consume caffeine regularly, your brain may even add more adenosine receptors to compensate, which is one reason people develop a tolerance and need more coffee for the same effect. Adenosine doesn't have dramatic behaviors associated with it like dopamine or serotonin do. Rather, it's this gentle accumulating force that eventually demands you go to sleep. It's crucial for regulating our sleep-wake cycle. The fancy term is homeostatic sleep drive. Without adenosine, we might forget to sleep and exhaust ourselves. In fact, experiments on animals where adenosine receptors were blocked long-term caused severe sleep deprivation issues, showing how important that signal is. So, next time you're pulling an all-nighter and your head feels heavy, that's adenosine doing its job, whispering, then shouting, "Sleep!" And when you reach for a late-night coffee or energy drink, you're essentially hitting the snooze button on that chemical alarm. Just remember, adenosine will eventually get its way. Our brains need to rest, and adenosine ensures that we do by making the call for sleep impossible to ignore. We've now met a lineup of neurotransmitters, each with their unique roles. Dopamine, the motivator and reward giver, critical for pleasure, learning, and movement. Serotonin, the mood stabilizer, regulating happiness, anxiety, sleep, and appetite. GABA, the calming brake, preventing overexcitation and keeping anxiety in check. Glutamate, the exciter and learner, driving neural activity and forming memories. Norepinephrine, the alertness and action signal, heightening focus and fight-or-flight responses. Acetylcholine, the learner and mover, enabling muscle movement and sharpening memory and attention. Endorphins, the natural opiates, easing pain and boosting euphoria and relaxation. Oxytocin, the bonding chemical, fostering trust, love, and connection. Histamine, the alertness maintainer. And Allergy mediator, helping keep you awake. Adenosine, the sleep pressure builder, making you sleepy as you stay awake and being counteracted by caffeine. It's amazing to realize that everything we feel and do has a chemical conversation behind it. But what happens when those conversations get garbled or out of balance? Let's explore how neurotransmitter imbalances can lead to various health conditions. When brain chemistry goes wrong. Imbalances and disorders. Neurotransmitters work best in a delicate balance. Too much or too little of a given neurotransmitter, or problems with their receptors, can lead to noticeable changes in how we think, feel, or move. In fact, many neurological and psychiatric disorders are now understood in terms of neurotransmitter imbalances or dysfunctions. Here are some examples of what can happen when these chemical messengers aren't working as they should. One major theory of depression is that it involves low levels of key neurotransmitters like serotonin and norepinephrine in mood circuits. People with depression often have a persistent sad or empty mood, fatigue, and loss of interest symptoms that correlate with reduced serotonin activity. As mentioned, medications like SSRIs that boost serotonin are common treatments, and SNRIs that boost both serotonin and norepinephrine can energize and improve mood. Depression isn't just feeling sad, it's often a reflection of a brain chemistry imbalance that makes it hard to experience pleasure or motivation. On the flip side, too much serotonin can lead to a dangerous condition called serotonin syndrome, usually only due to medication overdose, and has even been speculatively linked to certain symptoms in autism if present chronically high. While many brain chemicals play a role in anxiety, Low GABA activity is a common theme in conditions like generalized anxiety, panic attacks, and PTSD. If GABA's calming influence is weak, the brain's fear centers, like the amygdala, may fire off too easily, leading to excessive worry or panic. That's why treatments that increase GABA effects, benzodiazepines, certain anticonvulsants, can reduce acute anxiety. Overactive norepinephrine can also contribute to anxiety, making someone feel constantly on edge as if danger is everywhere. In PTSD, patients have an exaggerated fight or flight response, hinting at a hyperactive norepinephrine system, among other factors. This complex psychiatric illness involves symptoms like hallucinations, delusions, and disorganized thinking. The long-standing hypothesis is that overactive dopamine in certain brain pathways, the mesolimbic pathway, contributes to the positive symptoms like hallucinations. That's why almost all antipsychotic drugs work by blocking dopamine receptors. Newer research also implicates other neurotransmitters like glutamate. A glutamate dysfunction, possibly underactivity of glutamate in the frontal cortex, might explain some of the cognitive and negative symptoms of schizophrenia, like lack of motivation or emotion. Schizophrenia shows how complex brain disorders usually aren't about one chemical, but multiple systems going awry. Still, dopamine is the star player clinicians target for treatment. In manic episodes of bipolar disorder, people have excessively high energy, racing thoughts, and often impulsive behavior. Brain imaging and studies suggest too much norepinephrine and dopamine activity, along with abnormal glutamate transmission, are present during mania. It's like the brain's throttle is stuck wide open. Indeed, many treatments for mania aim to dampen these systems. Lithium, a classic mood stabilizer, can lower norepinephrine release, and antipsychotics used in mania reduce dopamine. Balancing these neurotransmitters can help bring someone down from a manic state back to stability. We touched on this earlier. Parkinson's is primarily caused by the death of dopamine-producing neurons in a region called the substantia nigra, leading to an 80% or greater drop in dopamine in movement-regulating areas. The result is the characteristic tremors, stiffness, and slow movement of Parkinson's. It's essentially a dopamine deficiency in the motor circuits. The main treatment, L-Dopa, aims to restore dopamine levels and thereby improve symptoms. This is a clear example of a direct neurotransmitter deficiency causing a disease. Interestingly, Parkinson's patients can also have depression or apathy as a result of low dopamine, showing dopamine's role in mood as well. We also mentioned Alzheimer's. Here, a major issue is not enough acetylcholine due to degeneration of ache-producing neurons. This contributes to the severe memory loss seen in Alzheimer's. So, boosting acetylcholine via cholinesterase inhibitors is a common therapeutic strategy to help memory, though it's not a cure. Alzheimer's is also associated with glutamate issues and buildup of toxic proteins, but ACE loss is one piece of the puzzle that we can address to some extent. Epilepsy or seizures occur when there's abnormal, excessive electrical activity in the brain. Often there's an imbalance between excitation and inhibition, basically not enough GABA or too much glutamate in certain areas, leading neurons to fire uncontrollably. Many anti-epileptic drugs increase GABA levels or effects or dampen glutamate to help prevent seizures by restoring balance. Even a high fever in children can tip this balance, as fever increases glutamate release, causing a febrile seizure. Chronic pain conditions aren't just about injury, they involve neurotransmitters too. For instance, in fibromyalgia, a syndrome of widespread pain and fatigue, researchers have found low endorphin levels in some patients, which might mean the brain isn't adequately suppressing pain signals. This could partly explain why things that normally wouldn't be very painful are experienced as painful, indicating a lower pain threshold. Such patients might benefit from exercise or therapies that boost endorphins. Chronic pain also involves glutamate, which is excitatory in pain transmission, and GABA, which provides inhibitory control, imbalances in the spinal cord and brain. Chronic insomnia can involve dysregulation of multiple neurotransmitters. Sometimes it's excess orexin, also known as hypocretin, or norepinephrine keeping the brain on alert, or it could be low GABA at night failing to quiet the mind. This is why various sleep aids target different chemicals. Some are antihistamines to block wakeful histamine, some enhance GABA like zolpidem, also known as Ambien, and some target melatonin, a hormone influenced by serotonin. These examples highlight a key point. When neurotransmitters don't function properly, specific health problems can emerge. It could be a production problem, like not making enough of a neurotransmitter or making too much, a reception problem where receptors are not responding or being blocked, or a removal problem where the neurotransmitter isn't cleared properly. Often it's a combination of factors. The good news is that understanding these imbalances leads to treatments. For instance, if too little of a neurotransmitter is an issue, we try to increase it, like giving L-Dopa for dopamine in Parkinson's or an SSRI to increase serotonin in depression. If too much of a neurotransmitter is the issue, we try to decrease or block it, like antipsychotics blocking dopamine in psychosis, or anticonvulsants inhibiting glutamate activity to stop seizures. If receptors are the problem, say destroyed by an autoimmune attack, as in myasthenia gravis for HH, or in some cases of depression where the receptors may be overly sensitive or insensitive, medications or interventions aim to bypass or reset those issues over time. It's a balancing act, and often multiple neurotransmitters are involved in any given disorder, which is why treatment can require a multi-pronged approach or some trial and error to find what works for an individual. A key takeaway here is that our mental health and neurological health have a real biological basis. Conditions like depression or ADHD are not moral failings or just in your head in the dismissive sense. They're in your head chemically, meaning something tangible is going on in the brain chemistry that can be addressed. This understanding reduces stigma and points to real solutions. We've now explored not only how neurotransmitters work, but also what happens when they go out of balance. From low serotonin in depression to dopamine overactivity in schizophrenia, from the calming powers of GABA to the fire-starting energy of glutamate, you've seen how brain chemistry, when disrupted, can shape everything from our mood and memory to our mental health. But this is just the beginning of the bigger story. In Part 3, we're going deeper into the good news, how you can influence your brain chemistry through everyday choices. Coming up next, we'll uncover how your diet, sleep, and exercise impact neurotransmitters, the surprising role of your gut-brain connection, how medications and supplements fine-tune brain chemistry, plus fascinating real-life case studies like why caffeine wakes you up and how exercise triggers a natural high. So, if you're ready to learn how to tune your brain like an orchestra, stick around for Part 3, Tuning Your Brain Chemistry. You won't want to miss it. And hey, if you're enjoying this series, don't forget to like, subscribe, and turn on the bell so you catch Part 3 the moment it drops. We've got plenty more tips and insights coming your way right here on Life and Learn. So stay tuned for more ways to help you grow, discover, and thrive.